Okay, good afternoon. So let's start today. We are going to show how we can improve differential codes using pure gaps in 2 points. So I need 3 lemmas before. Actually, one we did yesterday, so just remember today. So today is improving edge codes from pure gaps in 2 points. So yesterday we proved this lemma. So I just call lemma 0 that if you had A, B, and I divisors, if A is smaller than B and I effective, with the condition that the support of B minus A has no intersection with the support of E. So this is empty. So if you have this, then we proved that this function phi over LA. So we have here a quotient of vector spaces. So this is the Riemann-Roch spaces associated to the divisor A plus E. And so we have the quotient here. Also we have here. So we just proved yesterday this was injective. Okay. So in particular, we had, well, the dimension here is smaller than there. So what we want is that, so in particular, we have that we can write like this. The dimension of this minus the dimension of this is smaller than the dimension of B plus E minus the dimension of A plus E. Okay, this is this is the, this is A. So yeah, you are saying that the dimension of this, the Riemann-Roch space defined by this minus this, is smaller than this minus this, okay? So we had this, and today we need a second lemma to do the codes. So lemma 2, or lemma 1. So it's gonna tell you the following. Now you have, you have L and B divisors. You just suppose that B is effective and that the dimension of the Riemann-Roch space defined by the divisor L is equal to the dimension of the L minus B. So what we have is that if you take another divisor larger than 0, the effective divisor with support of E intersection with support of B. So E and B are positive divisors equal to the empty set. So you have no one in the intersection. You have no place that lives on E and B at the same time. Okay. Then what you have is that if you do minus E in both sides, you still have the same dimension. Okay. So This one we did the lemma 0 we did yesterday, so we just are going to prove this one now, and actually, well, we can use lemma 0 to do lemma 1. So we prove this, and then we need something else, to be ready to improve codes. So proof of this one. Oh, we want to prove this. So we have that this guy is smaller than this guy. This divisor is smaller than this. And we have that E is positive. And if you do these divisors less this one, you get the divisor this minus this, you have just B. So you have the support of B, that is the difference between these both, and support of I. Our hypothesis is 0. Oh, 0, no, it's empty set. So we are in condition to apply lemma 0. Okay? So by lemma 0, so we have like this will be A, this B, okay? So by lemma 0, what we get? You have something like this. We can just write down here. We have that this, and L minus B minus C, this quotient. And here you just do L of L over L of L minus E. Okay, so we have that this is injective. So this is our A on lemma 0. This is our B in lemma 0. This is our A in lemma 0. So this is injective, and so we conclude that we have that the dimension of this one of this minus this. And less this dimension. This is smaller than if I do this minus this. And this is larger than 0. And now by hypothesis, we have that these are equal. So this is just 0, because we are assuming this. So we get that these are equal to. Okay. So yeah, this is telling you if you have the dimension equal. Actually, you can take off another divisor and still have the same dimension if you take off a positive divisor with no intersection with this divisor B here, okay? So, and now, so we have this, and now we are going to prove the principal lemma we need to be able to improve the codes. So, lemma 2, let me just put here. I'd like to maybe to keep these lemmas on the blackboard, but I'm not sure. So, yeah. I think I don't remember if I'm gonna use this again. Let me see. Yeah, no. Yeah, so I don't need this again. So I just write the lemma 2 up here. So this is a result from HOMA and P, and they called it the dual series trick. So it says the following. You have divisors now L, M, divisors in your function field. And you have, so these ones you don't need any hypothesis on them, and you take another two positive divisors. So now you suppose that you have P, effective divisor, E, effective such that we have three conditions. So the first condition is when you do L plus M plus I, this is a canonical divisor on F. Okay, so this is a canonical divisor. Two, the dimension of M minus B is equal to the dimension of M, okay, of the Riemann-Roch space defined by M. And three, we also have the dimension of L is equal to the dimension of L plus B. So you have four divisors satisfying these conditions. So if this all happens, then we can conclude that the divisor B has degree is smaller than the degree of I. Okay, they were both effective, but this has to have a smaller degree than this one. And this is, actually, this is the result we are going to use to improve the lower bound on the minimum distance of the codes. So let's prove this. So I will start recalling the Riemann-Roch theorem. So recall that by Riemann-Roch theorem, we have that for any divisor A, the dimension of the Riemann-Roch space defined by A is just degree of A plus 1 minus G plus the dimension of W minus A, where W is any canonical divisor on your function fields. So, oh, we know that this guy is canonical. So you just write L plus M plus E. We'll write this like L plus E plus B plus M minus B. Okay. And now, well, you know that by hypothesis, this is canonical. So I can compute this dimension now. So I'm going to compute this dimension. So this is just the degree of L plus E plus B plus 1 minus G. G is the genus of the function field plus It should be now, it's the canonical that I'll take this guy is the canonical minus this one. So if I do this minus this, I have kept m minus b. Okay, so the dimension of m minus b. And also, I can compute the dimension of this. So this is just n degree of L plus E plus 1 minus G plus the dimension of who should be the canonical minus this one. So if I do this guy minus L plus E, I get just M. Okay? Now what we are going to do, we subtract this equation, one from each other. Okay, so we get that this dimension, this dimension is larger than this one. So this has to be larger than 0, minus this. So what we get now? Well, here I have the degree of L plus E, degree of L plus E, I do minus, so I keep degree of B. Okay, I cancel 1, G, and I get plus this minus this. Okay. And well, we have supposed that these are equal, so that is just 0. Okay, so this is just the degree of B. So or just like call attention to this, I have that, well, this Riemann-Roch space is contained on this one. And yeah, this is contained on this one. Okay, and we also said that the dimension, this is of the Riemann-Roch space on the left is equal to the dimension of this Riemann-Roch space. Okay, they are all finite dimension vector spaces. So actually what we have, since they are finite dimensional spaces, they are actually isomorphic, this guy and this guy. So we have this. Okay. What we want to prove? Well, we want to prove that degree of B is smaller than this. And here we have who is the degree of B. Now we just do the computation to the other side. So we have degree of B is equal to this dimension Yeah, so I'm doing the dimension from this space to this space. So this has to be smaller if I make the difference from here to here. So this is smaller if I just do the dimension from here to here. Yes. And well, we just saw that the dimension of this space is equal to this one. So I can just write this as the dimension of this guy minus the dimension of L plus B. So this is by 3. And when you have, well, the difference between this is always smaller than the degree of the first one minus the degree of the second one. So, and this is always smaller of the degree of this guy minus the degree of this guy. And then we keep what we want at the degree of I. So yeah, if you have divisors satisfying all this, you get this. Okay? So this is all nice. And now we are ready to prove the theorem. And well, we should have another blackboard, but I don't. So let me see what can I do, because I need to use that. Yeah, I will need to use both, so I have no idea. So I'll just put the statement of the theorem here. And well, before I put the statement, I just want to remember what does it mean to be a pure gap? We did yesterday. So let's just recall that being a pure gap, the condition was equivalent to say that the dimension of this space is equal to the dimension of this space. We have proved this. Okay. We are going to use this many times. So the theorem is the following. So let's alpha 1, alpha 2, beta 1, beta 2. Okay. In a square such that, well, you want that alpha I is smaller than beta I. Okay, for I equal to 1 and 2. So what you are saying is, okay, you are taking alpha 1, alpha 2 here, a point on the plane, and you want the coordinates beta 1, beta 2 be larger. So you have the other one to be a point like here. Okay. And what we are going to ask is that all the pairs inside this grid, all them have to be pure gaps. Also alpha 1, alpha 2. So alpha 1, alpha 2, this guy, and the guys in the middle. Okay, so what we suppose suppose that if you look to the set of K1, K2 for Ki between alpha I, beta I, well, all these pairs are pure gaps. At 2 points you have fixed your function field. Okay, here we don't have anything about being totally ramified. We have nothing. We have just these are just 2 points on the curve. We don't need anything else. Now you consider the divisor G to be this one. Actually, well, yeah, my notation now is just a Q1, Q2, so I just do like this, because otherwise I will, the notation will be different. So I have this, and I also take alpha 2 plus beta 2 minus 1 Q2. So let G be the divisor, and well, D, I wanted to define a code. So who's gonna be D? Well, D, you just sum certain PIs, rational points, different from this one and this one. Okay, so I want PI rational, degree 1. Okay, rational. And we want that PI is different from Q1 and Q2. So we want that the support of G and support of D have nothing in common. So we have this. Now we have G and D, we have a differential code defined by G and D. So then the minimum distance D of P omega DG code, AG code, satisfies the following. That so do you remember the classical bound was D has to be larger than degree of G of minus 2G minus 2. So this was the classical bound for any differential code. So now what we can add here is this number plus this number. Okay, so plus so we write like this. Well, because degree of G is actually this guy also, so it should be like 2 times degree of G here. But this is to make clear that this is the improvement. So what do you need if you want to do codes and get a nice improvement? Well, you need to find pairs of pure gaps here, like one here, another one, and so in such a way that they are really far away from each other. Well, the problem is that you need everything inside to be a pure gap too. And yeah, that's not so easy. Okay. So we are going to prove this, and then we are going to give an example over the Hermitian function fields. So proof. So, well, this code has minimum distance D. So what are you going to prove? Do you remember what is D? This is the minimum of the weight of all code words. So we are going to fix one code word with weight omega, and we are going to prove that omega is larger than this. So the minimum has to be always larger than this. Okay, so let let eta here, okay, not 0. So with weight omega. So how are the code words? We have to compute the residual of eta in P1, P2, Pn. I didn't say here, but who is n? Yeah, n is the degree of the divisor d, no? So pi is in f, and we are doing this for I equal to 1 to n. Yeah, is the length of the code. Well, so if it has weight w, it means that you have w coordinates that are non-zero and n minus w that are 0. So you just organize the coordinates. Okay, in such a way, we can say that the first ones are not 0 and the last ones are 0. So we can assume that the residual on pi of eta, this is 0 for I, this is different from 0 for I from 1 to omega. So I have omega here that are not 0, and that the residual in pi of eta, this is 0 for I from omega 1 to n. So we want to prove that omega is larger than this, huh? Okay. So, well, now there is a result we need to use, okay? That's the following, that we have that the residual on pi of eta is equal to 0. This happens if and only if when I compute the valuation pi in the divisor of eta, okay, this is larger than 0. Okay, so yeah, from here to here, it's clear. From here to there, yeah, you need a proof. Okay, so why is it clear in this direction? Just let's just remember why is it clear. So you have the place pi, so you take ti, a prime element at pi. Okay, so you can write locally, you can write your differential. It's just a function zi dti, let's say. Okay. And then what do you do? Well, you take your function zeta, you write it as a power series in this guy, ti, so it's going to be something like the sum from for I larger than n of A1, AI, Tn plus AI, okay, AIT, sorry, AITI, yeah. AI is in our base field, FQ or K. So, and N is here. And we have defined that, who is this guy? VPI in eta, by definition, was VPI computed in zeta I. Okay? And well, this is going to give the order of 0 or pole. So this is just going to be n by definition. So if this is n is positive, yeah, it means that the zeta is a function, has no pole at pi. And do you remember what was the residual? The residual was the coefficient a minus 1 here on this power series. So if n is larger than 0, a index minus 1 is certainly 0. So from this side to here, yeah, this is easy. It's just by definition, but to the other, then you need a proof. Okay, but we are going to use this. So we have this, and so what happens is that, well, you are telling that when the residual is 0, you have that VPI of eta is larger than 0. So what we get is that the divisor of eta, we had this before. We had that the divisor of omega is larger than G minus D. But now we know that divisor of eta is always larger than the residual is 0 from for I from omega plus 1 to n. So this is larger than, so I can just put like this. So I have this, and this is the sum of everyone. And since the residual is 0 for I from W minus 1 to N, I just have that actually this is larger than G minus the sum of PI's for I equal to 1 to N, to omega. Okay? This was the sum from 1 to N. But from omega plus 1 to N, I can just put 0 because of this. So I have this. And what is... Okay. So we have this, and we can write omega is larger than this, and now we are going to fit out everything to use the dilemmas, okay? So we are going to define, so let's, E by definition, it will play the whole of here. So just take this minus G plus the sum. So this is a positive divisor, okay? And it has degree. Oh, this is canonical divisors. So this has degree 2G minus 2. So minus degree of G. And degree here is omega. Okay. So I have this. And now we define also, we define L and M. So L for us will be alpha 1 minus 1 times Q1 plus alpha 2 minus 1 Q2. And M will be beta 1 Q1 plus beta 2 Q2 minus the sum from I to 1 to omega of the PIs. Okay. So yeah, we have nothing about L and M. They don't need to be effective. We just needed the E to be effective. So we have this. Okay. So well, if you what's gonna happen if you add these three divisors? Okay, you just see who is G. G is this guy. So G is just this part plus this part. So when I do this plus this plus this, I get 0. And this plus this one, I have 0. So when I do L plus L, I plus L plus M, I just have the divisor of the differential eta. So it's a canonical divisor. So we have the first condition. And now I have no blackboard anymore. Let's see. So I will go on here. Okay, so we have that I think if I do a smaller letter, you cannot see, no? I don't know if you can see well. So this is just Canonical. And now we need to prove 2 and 3. So, well, we still need to set who is B. So we'll do like this. Set B. B is defined as beta 1 minus alpha 1 plus 1, Q1, plus beta 2 minus alpha 2 plus 1, Q2. Notice that since we have alpha 1 less than this, alpha 2 less than beta 2, this is an effective divisor too. So we are still in the conditions of this lemma, okay? So claim 1, we need to prove this. We want to show that these dimensions are the same. Right? So okay, so let's do it. So we are going to define another divisor, L2. It will be the beta 1 Q1 plus beta 2 Q2. Okay, then if I do this, L of L2 minus beta, who I get? Oh, I have this guy minus this guy. So I have the dimension of alpha 1 minus 1, Q1, plus alpha 2 minus 1, Q2. Okay? It's just the difference. We get these guys. And now we go on our hypothesis. Our hypothesis is this. All the guys between alpha 1, alpha 2, beta 1, beta 2, they are pure gaps. So from this condition star, here, we have that this has to be equal to alpha 1, Q1, plus alpha 2, Q2. Okay? But now, I can add 1 again, because I have all the guys in the middle being a pure gaps. So I can just go like, I apply this again. Okay? And so what are you going to do? You are going to apply until you get to beta here. So you can do this till you get to beta 1 Q1 plus beta 2 Q2. And who was this guy? Yeah, this guy was L tilde. Right? So we have that for L tilde, this dimension is equal to this, to the dimension of L tilde. Okay? So, yeah, we come here. So we are going to apply now lemma 1 that I have erased. I have this dimension equal to this one. Now I'm going to take a guy with support nobody here on B. So you take this guy. Define beta tilde as the sum phi to omega of pi's. This is positive divisor. And yeah, and we have that the support of this guy and the support of L tilde is empty. Right? Because I have the pi's here, and here in L tilde I have Q1 and Q2. So I can apply lemma 1. The one so this is the erase dilemma. And what we conclude, that if I take off E, I still get the semi-dimension. Okay? So by lemma 1, I have that these dimensions are equal. Eta tilde has the right, satisfies the right conditions. So lemma 1 implies that I can just take off eta tilde from here. L tilde minus B minus this. This is going to be equal to this guy. L tilde minus eta tilde. This is lemma 1. Okay? Now we just need to check that actually what we have there, in one side we have this, and the other side we have M. So who is L tilde is here? Minus this guy. So this is just beta 1 Q1 plus beta 2 Q2 minus the sum of pi's till omega. Okay? Yeah, this is M. So this is M. And here I have to take this guy, it take off who else? I have to take off B. Who was B? Well, B is this guy. So if I do this minus B, what I get is alpha 1 minus 1 Q1 plus alpha 2 minus 1 Q2 minus the sum of pi's. Okay? And who is this? Oh, this should be and this is, okay, this is M. Oh, okay, sorry. I don't need to do all this. Huh? We have that, yeah, sorry. Yeah, this guy is M. So, yeah, so this guy is M minus B. Huh? Yeah, we don't need to compute again. Right? So we are done. Claim 1 is true. Huh? This dimension is equal to this one. For the divisor M and L chosen like this. So now we have to prove another claim is that this is equal also. Okay, so I'll just erase the proof of claim 1 and I will prove claim 3. Claim of this part. So just erase here, we don't need this anymore. We keep the divisors down here. Oh, I'll write here so I can save Blackboard. Claim 2 is that this dimension is equal to this dimension. Okay. So claim 2, who is L plus B? Now B is here, and L is over there. So if I just add L and B, I will get beta 1 Q1 plus beta 2 Q2. Okay, and L is just with the minus. Okay, this one. So we want to prove the dimension defined by this divisor is equal to the dimension defined by this divisor. But again, no, you have that alpha 1 and alpha 2 are pure gap. Alpha 1 and alpha 2 are pure gap. So you can jump from here. The dimension with these guys will be like this. But these are also pure gaps. So you can go to alpha 1 plus 1, alpha 2 plus 1. But these guys are pure gaps, so you can just go adding 1. So at certain point, we will achieve beta 1, beta 2. Okay. So, yeah, this is the proof of the second part, that this is equal to this. So our divisors E, L, and M chosen like this, they satisfy all these conditions. So you have that the degree of B is smaller than the degree of I. Okay. So, well, I'll put here. Huh? So by, okay, claim 1, this is done, this is done. So by lemma 2, we conclude that degree of B is smaller than degree of I. Now we just need to do the computation. So degree of B is this. So we have, so that is, so degree of B is here, is just, well, alpha 1, sorry, beta 1, minus alpha 1 plus 1 plus beta 2 minus alpha 2 plus 1. So this is smaller than degree of I. Degree of I is here. We have already computed. So this is 2g minus 2 minus degree of g plus omega. You see? So we get that omega is larger than degree of g minus 2g minus 2 plus the sum of beta i's minus alpha I plus 1. So if you take, what you are saying is that the weight of any code word in your code is at least this. So the minimum distance is at least this. Okay? And well, and we have proved this. Yeah, it's very, I think it's very nice result. No idea how they how they get here. Yeah. So so now we have this, and so well, can you use this in practice? Because if you are doing code in theory, yeah, sometimes you want to see the parameters of the codes. If you can prove the minimum distance, what can you do in real life? So we'll do an example over the Hermitian curve. Okay. I'll just erase everything, and then we do the example. Well, the points we are going to fix here, again, it will be, well, Q infinite and Q1. So, or we just call it Q0, who is it? Q0 is over P0, that means x equal to 0. So it's the root 0 here. It could be any of the roots, okay? We know that this place is totally ramified, so we are taking the place up there. So you want to do 2-point codes here. So claim 1 is that for A from 1 to Q minus 1. Here I need Q has to be at least, I don't know, 3 or 5, something. So yeah, let's put 5 to be safe. So here, and the B is from 1. So for A and B here, we have that AB is a pure gap at Q infinite, Q0. Yeah, so how we prove that? Well, we saw yesterday, we had an arithmetical condition to decide when a pair was a pure gap at Q infinite, Q0 in a common extension. So you can just apply that conditions, okay? So the conditions were these ones. I'll just copy here and then you just have to do the computations. So yeah, let me get the conditions. So the conditions are this one. We have that, so we need to prove so that, so AB is here. Do you remember what we did is, well, we looked to the Riemann-Roch space up and we wrote it as the direct sum of Riemann-Roch spaces in the rational function field, and we could use that to obtain these conditions. So the conditions is for T from 0 to M minus 1, M is Q plus 1, so for Q. So we have that this happens, or this is negative, or this is positive. And the second condition was this guy does not divide this up, and this guy does not divide this guy. So you take a T, you check. If it is negative, we are done. If it's positive, you need to check an extra condition. Okay, the second condition is like Q plus 1 does not divide I minus QT. And the Q plus 1 cannot divide also B plus T. B plus T, that's it. So what is happening here? Yeah. If you can prove this, what we have is, we have that for A from 1 to Q minus 1, we have gaps. Here, and I just put B1, okay, B from 1 to Q minus 2. Okay. So what we are saying is that What we are saying is all the pairs inside of this grid, they all are pure gaps if you prove that. So what we are going to do to get a code with large minimum distance? Well, we take one of the pure gaps here. Yeah, you choose one here and you choose the other one here. Right? So oh, sorry, I'm writing. No. Sorry, it's not this example, huh? Ah, yeah, it's not this one. Yeah, okay, the condition is okay, but yeah, when I saw the pure gaps, it's this example because this gives you a better, larger distance. So the condition here is a little bit different. The condition is that you want to take A from, so A is from Q squared minus 2Q minus 1 over 2. And Q squared minus Q minus 1 over 2. And B is from 1. And Q minus 1 over 2. Okay, so yeah, this is it. Yeah, that one was right too, but actually I'm going to do this example because we get a better distance. So yeah, so this is not one. Actually, this should be this is the guy Q squared minus 2Q minus 1 over 2. And this is the Q squared minus Q minus 1 over 2. And here is okay. So to get the code, we need to choose pure gaps far away from each other. So we take one here, we take this one here, and then we can do the code. So we need to prove this. Okay, so yeah. So let T so case one. So if T is from Q plus 1 over 2 till Q, we are going to prove that in this case, this is always negative. Okay, so what we have something like A minus this over Q plus 1. Yeah, M is Q plus 1. Plus this over Q plus 1. So, well, the largest value for A is this one. So I have something like Q squared minus Q minus 1. I'll just put down here 2Q plus 1. So I just put minus 2 QT. Okay, QT. And well, for B, we have that B, the largest value for B is this guy. So we have this is at most Q minus 1 plus T plus 2T over Q plus 1. Okay. And well, so I can now so T is always larger than this, so it's always minus T is smaller than this, so I can just put here Q squared minus Q minus 1, and we just take now T equal to Q plus 1 over 2. Okay, so we have 2, 2, so minus Q minus 1. Q plus 1. And here, the largest value of t is just q. So here I get q minus 1 plus 2q over q plus 1. So this is, I just need to do some computations. There's no way to. So I can write this like, so the square go away, I get minus q, so I get minus 2q minus 1 over 2 times q plus 1. And I get 3 times q minus 1. And I can write this like, this is just 2q plus 2 plus q minus 3 over this. Okay, so this is just, well, this is minus 1, yeah, because it's 2q plus 2, this is minus 2q minus 1, so this is minus 1, and this is just, I think oh, yeah, okay, sorry, this was 2 here. Yeah, it was missing a 2 for me. So yeah, this was 2. This is 2. Now I'm happy because here is 2. Otherwise, so yeah, so this is minus 2. This is good. And this is, you have 1 plus q minus 2 over this is 0. So plus 1, this is minus 1. So you see, this is always less or equal than minus 1. So you are in this condition, you are done. Okay. So we have the other case. So it should be from 0 to q minus 1 over 2. Oh, actually, well, I don't need to check. I will not check this. If it's negative, we are done. If it's positive, I should check this. So I'm just going to show that this is not happening. And then we are done. Okay? So for this, what we have, so that q plus 1 does not divide b plus t, and q plus 1 also does not divide a minus qt. Okay, so for b, what we have? Yeah, so b is from 1 to q minus 1 over 2. So if I add t, right, b, so this will be, if they both 0, 1, so this should be 1 at least. And this is at most q minus 1 over 2 plus q minus 1 over 2, at most q minus 1. Okay, so yeah, this is not a multiple of q plus 1. So, yeah, when you have already the pure gaps, you look and, well, it's easy to prove. But what usually is the problem? The problem when you do these things is to find the pure gaps to test. So the problem is how to guess the pure gaps. So usually you need to do some some tests with magma, do some computations, because if I give you an algebraic curve and I ask you, well, give me a grid of pure gaps, that's not so easy. Okay? So we have this, and now if I take, now look, we have a here, So we can just write like this. Okay, so we can just write that numbers in terms of q plus 1. So you can write the first one like this. And the second one you can just write like this. Oh yeah, this guy is just this guy, and the other guy is just this guy. So you see, so I can just write A is just equal to q plus 1, q minus 3 over 2 plus a certain A1 for A1 between 1 and q plus 1 over 2. Yeah. So now we have that q plus 1 divide A minus q t, if and only if q plus 1 divides A1 minus qt. Okay, and now you just need to check this, and let me see if I do another trick or not. Yeah, so A minus. So, yeah, and yeah, okay. And this, you see, I can write this like this. And we just have to play a little bit, so it should be minus q plus 1t. Yeah, so I put just minus t, so I need to put plus t. So q plus 1 divide this, if and only if, and that's it. Q plus 1 divides A1 plus t. But we have A1 here, and we have t between 0 and q minus 1 over 2. So when we add at least 1, and at most I don't get q plus 1. I had something smaller than q plus 1. So for sure, q plus 1 does not divide this guy. And we are done. Okay. So all these guys are pure gaps as we wanted. So claim 1 is proved. Okay, so now you just let G to be alpha 1. So okay, let's do this. So I'll do like so this will be just q squared minus 2q minus 1 over 2, 1. And we just do beta b1, beta 2 equal to like q squared minus q minus 2 over 2 and q minus 1 over 2. So you have this. So just put G as before. I'll just copy here because, well, it's a bunch of calculations. So this is like q squared minus 3q over 5 over 2 plus q minus 1 over 2 to 0. Okay? Well, this is the divisor G, and so you take D. Well, you can take all the other places over the Hermitian function field, and you just let 2 away. The Hermitian function field has q to the cube plus 1, so I take 2. So I get, well, D should be the sum of pi rational, and different from this and from this. So degree of D is just q to the cube minus 1. Okay, so you have a code of with this length. And what can we say? So the minimum distance by the theorem or from, we know that, well, the minimum distance of the code has to be larger than degree of G plus minus 2G minus 2 plus the sum of, should be beta, what? Okay, should be beta 2 menos A2. Right, just beta 2. E mais and yeah, that 2 minus A2 plus 1. Okay, so yeah, one of these is just a q plus 1 over 2, and the other one is just a q minus 1 over 2. So when you add, you get q. So you get an improvement on the you have the classical bound, this one, and you can improve the classical one by q. So yeah, for larger q, you get well, you get a better improvement, but it's not really true because your code is also longer. So yeah, you should do relative parameters to this. So well, this was the example I want to show. I hope you enjoyed it. There is a lot of literature on this. If you want to go on, okay, just look for Kummer extensions, pure gaps, and oh well, there is a nice paper, a new one, where actually they computed all pure gaps in 2 points in a function field. Okay, so they used that bijection between the gaps that you obtained when you look to the graph of this gap. They use this bijection. There is another way to look to the pure gap is using this bijection. You can see the pure gaps from this, and then well, they characterize all them on function fields. It's a work from well, Eric, Alonso, and Guilherme. Okay, so well, Mendonça, Castellanos, and Chiziote. So thank you very much, and I hope you enjoyed it. And well, see you.